Today I'm gonna talk about the sea ice surface temperature from seabed passive microwave observation, and my colleague Suman contributed to this work, and I should also mention that Emmy and Ida and Pia and Jakob also contributing to this project together. And yeah, and as Jakob already explained a few minutes ago, there is two different kinds of sea ice surface temperature in sea ice system. The first thing is the snow surface temperature, and the second thing is the ice surface temperature, the real ice surface temperature. And if we use infrared observation, we can get the air snow surface temperature, but the satellite observation of infrared ice surface temperature is quite accurate, but it is always blocked by cloud cover, and so it has not good spatial coverage. But on the other hand, the passive microwave ice surface temperature represents the snow ice interface temperature, and that's less accurate, but it enables more frequent and complete monitoring of ice surface temperature field. And so we're expecting a new satellite in few years. So yeah, and it's called Copernicus Imaging Microwave Radiometer, and CIMR is called as like CIMR, and CIMR is being developed by ESA for launch in late 2020s, and CIMR will improve measuring sea ice and polar ocean at higher spatial resolution and accuracy. And as you can see on the left bottom figure, the CIMR has the much more smaller footprint compared to the AMSR or SSMIS, which is previous passive microwave imagers. And there is a ESA-funded project called CIMR Level 2 PAT. That project is to prepare polar oceans and global land Level 2 algorithm for CIMR. And if all the software data algorithm documentations will be available to the public for free of use. So if you want to learn more about this project, you can scan this QR code and go to the GitHub page, and you can find everything. It will be open in a few months, I guess. And I will briefly introduce how we can actually retrieve ice surface temperature from the band observation. And there are three key assumptions for baseline algorithm. The baseline algorithm is introduced by Lee and Son 2015. And the first assumption is that snow ice interface is an effective emitting layer for seabed. And if you see the plot in the left hand side bottom, and the x-axis is brightness temperature of seabed observation, and y-axis is the emitting layer temperature for seabed. You can see it is very highly correlated, and there's almost one-to-one relationship. So that's the theoretical basis of retrieving IST from microwave seabed. And the second assumption is that the atmosphere and snow layer on sea ice are almost transparent as seabed. If you look at the second figure, it shows the extinction coefficient of atmosphere, and if the very left part is the 6.9 gigahertz, which is seabed, you can see the extinction coefficient or the transparency of atmosphere is very high in the Arctic condition. And also the scattering effect is also very minimal. I will not go into detail about the right-hand figure, but it tells us that you can neglect the scattering effect in seabed for atmosphere. And the last assumption is that the sea ice surface is specular at seabed, which that means the sea ice surface is very smooth for the lower frequency, and its reflectivity can be described by Fresnel equation. And I guess most of you know about Fresnel equation, but in short, it describes the reflectance of specular surface, and the equations are given in the right-hand side. And what we need to calculate reflectivity using this equation is the incident angle and the refractive index of ice. So that's why the reflectance becomes a function of n refractive index and theta, the incident angle. And my previous colleagues Song and Lee developed a combined Fresnel equation, which is the combination of those two equations, and you can remove theta dependency from that. So the relationship between vertically polarized reflectance and the horizontally polarized reflectance are just a function of it removed the refractivity. Sorry. And so it's only a function of incident angle. And we know the incident angle for our observations, so it is possible to relate those two quantities. And another key part is the emissivity plus reflectance is equals to 1. So that describes the energy conservation. And here is a radiative transfer equation that is used for the retrieval. And the left-hand side, there's a T-P theta, that's the brightness temperature that will be measured by satellite at incident angle theta and polarization P. And the T up is the upwelling brightness temperature from atmosphere. And the second term, epsilon Ts tau, is a surface signal that emitted from ice surface. And the third term is something related to the surface reflected, the downwelling atmospheric radiation. So what we want to know is Ts here. And so this is the most trickiest slide. So you will be free in 1 minute. So yeah, if we rearrange this equation, we can have, you don't see my mouse cursor, so we can write the emissivity and in these two equations. If we make a ratio of those two equations, we can remove the denominators, and what we only need to know is the RH, and we can find RH by comparing the theoretical curve and observation, and we can find intersection and find RH, and we put RH again to this equation, and we can find a solution for TS. If you want to know more about this, you can just approach me and ask details about it. So this is the demonstration. So we used input data came from answer 2, 6.9 gigahertz observation, and we also use ERA 5 atmospheric profiles, and we put those atmospheric profiles into ArcTIL13, which is developed by the UMaset, the NWP SAF, to get the TU, T up and T down and tau. And so you can see the retrieved sea ice surface temperature on the right bottom corner, and all the 5 panels are the input data used for retrieval. And so it is also very important to quantify the uncertainty and the accuracy of the product. And we have a validation plan by comparing the retrieval with the buoy measured temperatures. So as Jakob already showed you, there is a thermistor string observation over the Arctic, and we can extract the snow ice interface temperature from that observation. And it is very straightforward to make a comparison between them. So now we are creating a matchup data set between AMSR 2 and buoy and ERA 5 atmospheric profiles, and it will be available in a few months, I guess. And we have some future research and development plans. And the first thing is the bias correction method. And we expect there must be some systematic bias in our retrieval. And not only C-band, but there's also the higher frequency informations, and that will deliver us some snow condition or temperature, or some more information about that. We believe that those information can be used to correct systematic bias that we expect from it. And before CIMR becomes operational, ANSWER2 will be used for the development, and the developed correction method will be updated with CIMR observation afterward. And here's some application examples. And I got some questions about why do we care about ice surface temperature? And I think these slides can provide some answers to you. And first of all, there is this sea ice surface temperature can be used to estimate sea ice emissivity for several frequencies. And if we can get some emissivity, it can be used to differentiate different kinds of sea ice types. You can see the left. And Lee et al. 2017 paper. And also, it can be used to estimate sea ice thickness and snow depths as it gives you some information about snow depths. And also, the modelers also require some information, temperature information to constrain their model. So on the right, you can see the warm bias in the sea ice model has significantly improved when both infrared infrared IST and microwave IST was treated to the ice model. And the one last thing is that maybe we can use microwave IST to supplement the infrared IST, because you already saw that there's cloud everywhere, so there's many gaps. So we think that the passive microwave IST could be a good predictor for filling those gaps. And thank you for your attention. And yeah, any questions as well.
Thank you, Hoyeon, for a very interesting talk and giving us the basis for IST from passive microwave. We await the questions to the question session after the next talk. So we then go to Hoyeon Shi from Northwest University. We'll give an